Okay, so hopefully we're all ready to keep talking about the kidneys. Okay, so we now know some of the general roles of the kidney. Last time we talked about how we get fluid into the kidney and specifically into the first parts of the nephron. So we were talking about our glomerular filtration pressure, our glomerular filtration rate, and how exactly it is that we have so much fluid running into the nephron, along with all the dissolved solutes that we're going to see in there. So the next thing we want to think about as we think about the kidney and how this is working, so we want to be attentive to the adjustments that we're going to be making to that filtrate that we're pulling into the nephron. So that fluid, that plasma with all its dissolved solutes, we're going to be making adjustments. So we're going to be moving things from that filtrate back to the blood, back to the peritubular capillaries. That's our reabsorption. We're going to see secretion. So we're going to see things moving from elsewhere alongside the nephron and adding extra stuff into that filtrate. We're going to see excretion out the end. So we see that fluid leaving the kidneys, going to the bladder, being excreted out of the body. So one of the really key things we want to be clear on is this process of reabsorption. So reabsorption is any movement from inside the tubules, so from inside the nephron, into the peritubular capillary. So that part of reabsorption is we're returning this stuff to the bloodstream. So most of this is going to happen in the proximal tubules. That's the part right after we leave Bowman's capsule and Bowman's space, where we're catching that filtrate from the glomerulus. We start to have this twisty first proximal part of the nephron. That's where most of our reabsorption is happening, but not all of it. So most of our reabsorption, we're going to refer to as unregulated. When we say not regulated, we don't mean that it's never going to require any energy. What we mean is that this is not happening because we have some kind of hormone signal or nervous signal from elsewhere in the body. So most of this is happening kind of automatically. You almost want to think of it. So when we think about this reabsorption in the proximal tubule, so in this first little section of the nephron, we're going to want to think about what cell layers we have to cross, essentially. So when we're thinking about reabsorption in the proximal tubule, we're going to be crossing the epithelial cells of that nephron. So the lining cells, essentially, of that proximal tubule. Those are our renal epithelial cells. We're also going to have to cross the wall of the capillary itself. That peritubular capillary lying alongside the nephron is also contained by a layer of cells. So those are our capillary endothelial cells. Good. So we are going to be reabsorbing lots and lots of stuff in the proximal tubule. We're going to think of it as our mass reabsorber later on. So that means lots of water and lots of solutes. So most of this stuff is going to be happening with the assistance of sodium. So we remember our sodium-potassium pump is a way that we set up a sodium gradient where we have low sodium inside a cell, higher sodium outside the cell. Then we can use that gradient to power secondary active transport of other molecules. So we're going to see a lot of sodium involvement when we look at reabsorption in the proximal tubule. And one of the key things to notice is we have lots of things that we're filtering at the glomerulus and then reabsorbing later on, particularly in the proximal tubule. Some of these things, we're going to reabsorb almost all of it. So here you can see that water, we're going to take back 99.2% of that water that we filtered out with the plasma and return it to your bloodstream. So this is immediately how we're going to not immediately faint as our kidneys are filtering our blood. We're going to keep our blood volume up by having all that water reabsorbed. You can see glucose, right, is basically food for our cells, right? We use glucose to make ATP. So we're going to try to get 100% of that glucose back into your bloodstream, even though we do filter it out at the glomerulus. But we can see other molecules. We may be taking back variable amounts. For example, here our urea, we're taking about 50% of it back into the body, reabsorbing it. So in the proximal tubule, lots and lots of reabsorption happening. So 70% of the sodium in the water that you're going to be reabsorbing is going to get reabsorbed here in the proximal tubule. Okay? And 100% of the glucose that you're reabsorbing is getting reabsorbed here at the proximal tubule. So we're doing most of our reabsorption here, but we will see some more reabsorption later on for some of that sodium, for some of that water. So part of the reason that we can reabsorb so much is the structure of the cells. So reminder, the top of our cell, we have our apical membrane. So this is going to be touching our filtrate. Okay. Our basolateral membrane faces the blood at the base. Okay. Oh, these were labeled, but that's fine. Basolateral. I'll just write basal. This is our blood side. You'll notice that this apical membrane here, we have this brush border. So like literally it looks like a brush, right? See how squiggly it is, all these bristles, right? This means we have a really large surface area for things to come into contact with that apical membrane. They have to come into contact with the apical membrane in order to cross the cell to get back to the blood so that they're fully reabsorbed. It's also the case that between our cells, our tight junctions are not really so tight. Okay, so these little coffee bean things, those are tight junctions in this image. So those hold neighboring cells together, hold them sort of sealed, right? We're keeping that filtrate in the nephron, but they're going to allow for some paracellular transport. So some transport is going to happen kind of next to the cell across that leaky tight junction. Okay. So first thing you want to remember about reabsorption is the direction, right? So direction for reabsorption, it's going from our filtrate back to the blood, right? So that's our reabsorption direction. So we can see that we have sodium-potassium pumps here on the basolateral membrane. These are setting up a sodium gradient that's going to allow us to pull things in this direction, in this reabsorption direction, right? So this is why it's important to realize that unregulated doesn't mean no energy, because everything you see right here requires cellular energy, right? This is active transport. The sodium potassium pump uses ATP. So that's primary active transport to set up this sodium gradient. We have low sodium here in the cell, right? Which means we now have a sodium gradient to work with. So we can see our secondary active transport pulling glucose in, right? So now sodium is moving from high to low, pulling glucose with it, right? And you can see what's happening with the sodium here. That high sodium that we created in the peritubular fluid is going into the plasma. We'll see that this has also created a glucose gradient once we do this. Once we do this active transport, we now have higher glucose levels in these cells. So we can then use that on the opposite side to move the glucose towards the blood. Okay. So unregulated doesn't mean no energy. Reabsorption means towards the blood. So as we're thinking about this reabsorption, we are going to be thinking about how much can we reabsorb? What kind of limits do we have on this? So looking at that slide, I want you to imagine that sodium glucose transporter where we had that secondary active transport happening. Imagine it takes literally 1 second to move that glucose molecule into the cell. So I want you to imagine that. And then I want you to imagine you have 3 glucose molecules wandering by this cell. They've been filtered out from those glomerular capillaries. They're wandering past this cell. I want you to take a guess of what's going to happen with that transporter. Take a look. Okay, so this is setting us up for our next idea, this idea of a transport maximum. So what we're going to encounter as we're thinking about reabsorption in the proximal tubule, we can't go backwards from here. Once we have moved from the glomerular capillaries, gotten filtered into Bowman's capsule, we're just kind of there. We have to keep moving down the nephron. So now that we're passing these cells, these renal epithelial cells in the proximal tubule, we only have two options, right? So we can cross those epithelial cells and the capillary endothelial cells and go back to the bloodstream, or we're going to keep going down the nephron, eventually end up in the bladder, end up being excreted as urine, right? So the reason that the transport maximum exists is that we don't always have enough proteins embedded in those apical membranes, enough transport proteins embedded in those apical membranes to handle everything that we're shooting past through that proximal tubule. So we've got enough to manage normal levels, normal concentrations of these important molecules, but there is a point where your kidney just can't handle that much of anything. Particularly, we're going to be thinking about glucose. This is often something that we look at glucose for because glucose should be completely reabsorbed in the proximal tubule. So under normal conditions, normal blood glucose levels, you've got enough transporters in those proximal tubule epithelial cells to suck all that glucose back into your bloodstream. But in the case of diabetes, for example, where you may end up with really high blood sugar levels, you're going to hit a point where you can't do that anymore. You can't grab all that glucose back. So that's what's up with this transport maximum. So the transport maximum is the rate of transport when those characters we think of as getting saturated, right? So saturated, they're totally full. There's no extra room, okay? So that's our maximum rate for transport of, in the example we're going to work with, glucose, okay? So what we're imagining is a situation where we've got our cell, right? Worst cell I've ever drawn? Probably not, but close. Okay, so we've got some transporters here, some carrier proteins, right? We have glucose coming past, right? And if we have too many, right, we're going to hit that transport maximum, right? So the transport maximum is when we're transporting through all of those carriers, right? And if we go over, we're going to end up with spillover of whatever that is in the urine, of our glucose in the urine. So there are other ways we can think about this or talk about this or measure this, all of which kind of come together to give us the big picture. Okay, so what the renal threshold is, it's related to this transport maximum. So the renal threshold is going to be basically an amount of this substance in your plasma. So this is going to be like a plasma concentration of glucose, right? So that is the threshold. So threshold is like the edge of a doorway, right? So your renal threshold is going to be the amount of blood glucose that would match that transport maximum in the kidney, right? So this is going to be how much you can handle, actually reabsorb it all, given the number of carrier proteins that you have in the proximal tubule. Okay. If you go above that renal threshold, then you're going to end up with spillover in the urine because you hit the transport maximum of those carriers. Okay. So for our glucose, it's freely filtered at the glomerulus, which is to say that it's just coming through along with our fluid. We don't need any special mechanisms to filter glucose from the plasma into the nephron. It gets in there just along with everything else. Normally, we absorb 100% of it in the proximal tubules, returning that glucose to the bloodstream so you can use it to make ATP, which means that usually there's no glucose in your urine. If you do see glucose in the urine, then that means we have some spillover here, which probably means that you have a really high blood glucose level. So way back in the day, apparently it used to be a test for diabetes, like they taste urine to see if it was sweet. I truly cannot imagine a doctor actually doing that. So this feels a little bit like a rumor, but this is why you could do it if you wanted to. That excess glucose appearing in the urine is an indication of excess glucose in the blood. Okay. So for our carrier proteins for the glucose reabsorption, we saw that we're doing this by taking advantage of a sodium gradient that we set up with our sodium-potassium pump. So at the apical membrane, we're using that sodium gradient, which means this is secondary active transport. Across the basolateral membrane, once we have a high concentration of glucose in the epithelial cell, we've got a glucose gradient that we can use on its own. So it's going to be passive from high glucose in the cell to lower glucose as you approach the blood. But glucose is big, so you need a protein. So it'll be facilitated diffusion. Oh, gee, what happened there? Okay, cool. So let's think a bit more about this with pictures. Okay, so here we can see where we set up that sodium-potassium gradient. So here's that secondary active transport again of glucose across the apical membrane. All right, secondary active. And here's that facilitated diffusion. So the arrow is green because this is passive direction. So that's that facilitated. That's why we have this little circle. That's another membrane protein. Okay. And we can use this to think a little more clearly about these ideas of transport maxima and renal thresholds, right? Okay. So a typical plasma concentration of glucose is 100 milligrams per deciliter. So we've mentioned this number before. When we talk about filtered load, we talked about the fact that for our filtered load, we're really just multiplying a plasma concentration times our glomerular filtration rate. So times the amount of fluid, essentially, that's coming into the nephrons of the kidney every minute. Okay, so for our filtered load for glucose, because our typical glomerular filtration rate was 125, just multiply across, filtered load of glucose is 125 milligrams per minute. So that's how much glucose we're thinking about coming here through the tubular fluid, right? So your transport maximum for glucose, so the amount of glucose we can do this with, right? You can literally pull across, is 375 milligrams per minute. So that's totally fine if your filtered load is 125, right? You can definitely, absolutely handle that with a transport maximum of 375 milligrams per minute. You've got lots of extra room for your glucose level to go up. Okay. So your renal threshold, theoretically, is about 300 milligrams per deciliter. So the renal threshold, what we're thinking about to get to the transport maximum, all right, so the transport maximum was how fast can we pull that molecule back into the blood? How fast can we reabsorb it? All right, so you're going to take your glomerular filtration rate, multiply by your renal threshold to get that transport maximum, which means that to find the renal threshold, we can do it the opposite way. We could take our transport maximum and divide it by the glomerular filtration rate to get the renal threshold. I'm not going to ask you to do that math on the exam or any of our, future assessments, but it is helpful to think about that relationship. So our theoretical renal threshold is going to be 300 milligrams per deciliter. So what we're saying is that if we multiply our glomerular filtration rate times that number, times that amount of glucose in the blood, that's what's going to get us to hit this transport maximum. Does require some playing with our units and numbers because you'll notice this is per deciliter, right? Whereas that's not always what we have our numbers in. Okay. So theoretically, you should be able to handle a blood sugar level of 300 milligrams per deciliter. It happens to be the case that if you observe this in actual patients in real life, that's not what we really see happening, right? So usually we don't see your body functioning completely efficiently up to that theoretical renal threshold. Usually we see an actual renal threshold that's a little bit lower or maybe kind of a lot lower. So our actual renal threshold, so the actual glucose level where we start to see spillover in the urine is about 160 to 180 milligrams of glucose per deciliter of blood plasma. That corresponds to a filtered load of about 225 milligrams per minute when we calculate it out. And the reason for this is kind of statistics, kind of physics. So the issue is, if you imagine these transporters all here, right? So imagine we have a bunch of them. To get to your theoretical renal threshold to handle that with this transport maximum, that would mean they get 100% saturated, right? So like every one of them is operating all at the same time. But you have glucose. If you have a lot of glucose, there'll be some that's here next to the apical membrane, but some will be kind of in the middle. And if there's only like one little transporter empty along our proximal tubule and all the rest of them are full, the chances that your excess glucose is going to run into that specific membrane protein kind of lowers as you start to get to these higher levels. So we got a little bit of an efficiency problem here, but we still can handle our typical normal plasma glucose levels just fine. So remember, those normal plasma glucose levels are about 100 milligrams per deciliter. So even with this lowered actual renal threshold of about 160 to 180, we still should be able to reabsorb all our glucose. So here is a diagram kind of combining some of these concepts. So we're going to take a look what's going on here. All right. Okay. So what we're looking at is what happens as our blood concentration of glucose goes up. All right. So here is our plasma concentration of glucose. So that is how much glucose is in your bloodstream. And on our y-axis, we see the rate of glucose movement. So how fast is glucose moving? And for moving, most of what we're interested in is going to be this reabsorption part. So this moving back into your bloodstream. Okay. But we'll see an interplay here. Okay, so for the first little bit, your normal concentration of glucose is supposed to be about 100 milligrams per deciliter. So under these conditions, right, your bluish line here is your filtration. So that's how much glucose is coming out of the glomerulus into Bowman's space and then starting to move into the proximal tubule. And so we can see that that is directly matched here by this purple-pink line right under it, right? So that's our 100% reabsorption. So as we see our plasma concentration of glucose goes up, more glucose gets filtered into the nephron, but that's fine because your nephron can handle it. More glucose is also being reabsorbed back into the bloodstream. Okay. So the transport maximum, we can see here, the transport maximum is when we hit the maximum amount of glucose that we can move back into the bloodstream. All right, so you can see that our reabsorption rate for glucose can never go above that line because that is the maximum, that's it, that's full saturation. Okay. So for our renal threshold, here we're looking at the actual renal threshold, you can see this point where we start to have our glucose filtered levels just going up and up and up, right? Because we're just multiplying the plasma concentration of glucose times the glomerular filtration rate. So that's just a straight line, goes up forever. But we're starting to hit this point where some of that glucose isn't coming into contact with an unoccupied glucose transporter. So it's passing by the proximal tubule. So this is why we see that reabsorption start to kind of peel away, leaving some room between our filtration line and that reabsorption line. because all of our handling of glucose is supposed to happen here in the proximal tubule, and we're supposed to reabsorb it all, the rest of your kidney, the rest of the nephron doesn't have a way to make up for this, which means that all of that glucose, that spillover glucose, is going to end up in the urine, right? So if we matched up this difference here that we see, right, we'd see that that matches up to how much excretion we have on the opposite side. So that's our spillover glucose ending up in the urine. All right. So you can see this is a kind of slow peel away of these numbers, right? And that's why we have that difference between the actual renal threshold, which is where we start to see spillover, and the theoretical renal threshold would match up to like where that plateau is, where that plateau starts. But we don't immediately turn a corner and end up on that plateau. We kind of start to see this process becoming less efficient as we get there. Okay. So reabsorption is the return of filtered molecules to the blood. We were just looking at glucose reabsorption, but we reabsorb lots of other things. In particular, we also think about reabsorption of water. That's going to be one of the other main themes of this unit of the kidney, because we know that we have tons and tons of water in the plasma, right? It's one of our two types of extracellular fluid, lots of fluid. We have a high glomerular filtration rate. We had high glomerular filtration pressure. We were taking 180 liters of water into those kidneys per day, but we're only excreting a liter or two out as urine at the end, okay? So there'll be some variation here depending on your hydration state. So if you're very hydrated versus if you're dehydrated, your kidneys are going to operate a little differently. We'll see some regulated reabsorption of water in the more distal parts of the nephron, okay? But for now, we want to know that the proximal tubule is doing lots of this water reabsorption. Proximal tubule is doing unregulated water reabsorption. So we can use energy, but we don't need any hormone signals here. We are going to see that no matter how much you do or don't drink, there is a minimum amount of water excretion per day. So you need about 400 milliliters of water per day to come out as urine in order to not be like trying to urinate out like pure salt crystals, right? We need something for our waste products to be dissolved in. So about 400 milliliters have to be excreted, obligatory water loss, in order to get rid of the other toxins that are building up here. Okay. So we said about 70% in the proximal tubule. If we add in our loop of Henle, which we'll talk about in a little bit, we get to about 85% of our water reabsorption occurring in this total kind of first segment of the nephron, which I may just draw again. All right, okay, so Bowman's capsule is this top part of the nephron. Proximal tubule is just the first part. That's what proximal means. The loop of Henle starts to turn down. All right, so descending loop of Henle just means the descending part of this loop, the down part. All right, so these are the two locations we're talking about here. All right. So when we think about this unregulated water reabsorption that's happening, especially in the proximal tubule, we're going to think of water as following solute reabsorption. Our main solute that we're going to be interested in is sodium. Sodium is doing all sorts of things everywhere in our body, so that's probably not a huge surprise. So that sodium is being actively transported, so using ATP, across the basolateral membrane. So we saw that with the sodium-potassium pump. We didn't draw in the ATP, but we know it's there. Okay. And this actually establishes what we refer to as an osmotic gradient for water reabsorption. So an osmotic gradient, remember when we think about osmotic pressures, when we're thinking about Starling forces, we're thinking about a pull on water, right? So moving these solutes, moving sodium, is part of what's helping us establish a situation where we have a pull on water from the structures outside the nephron, okay? So we're going to be thinking about water following these solutes. So we actively transported sodium back to the blood, right? So actively means using energy, but this is still unregulated because there was no hormone involved. Chloride ions are also being transported out of that filtrate, so they're another solute. This one, you don't happen to need energy to do it. Their usual concentration gradient works fine, right? And then by osmosis, right? This means we now have a situation where we have lots and lots of water in the tubule. We don't have as much water outside where we have this buildup of chloride ions and sodium ions. So the water follows it, trying to reach equilibrium with those structures neighboring the nephron. Okay, so that's literally just osmosis happening here, really. Okay. So we can think about this in a bit more, I don't know, formal terminology here. Okay, so when we do that, what we're saying is that the osmolarity of the filtrate in the glomerular capsule, right? So osmolarity, oops. Okay, so we're saying, here's our glomerulus, that's our capillary going in. Here's Bowman's capsule around it. All right. So what we're saying is that at this first part of the nephron, the osmolarity of our blood plasma and the filtrate right here is equal, right? So we have the same concentration of everything right here, right? So that's our isoosmotic situation here in our glomerular capsule, okay? So we don't yet have an osmotic pull on water when we're right here, right? Now, as we travel down that proximal tubule, right, we're changing that situation. I'll just make it straight for a second. All right, so as we are moving sodium out, right, so as sodium goes out, right, so we reabsorb some sodium. This means that we now no longer have this isoosmotic situation, right? So we've increased the osmotic pull here next to our nephron, right? Now we have a more watery environment in that tubule than we do neighboring the tubule. So now we have an osmotic pull on that water. So that's what we see kind of happening in these images, is looking at that solute reabsorption. So basically, we're just setting up a concentration gradient of sodium. Part of what that does is pull water. Part of what that does is create a sodium gradient that we can use for secondary active transport of things like glucose. Okay. And this is just this same picture that we keep seeing here, right? So we see that basolateral membrane side. I'm not really sure why your book likes to use X and Y instead of just telling you exactly what we're talking about, but got our apical membrane facing our solute, or sorry, facing our tubular fluid, basolateral membrane facing the blood. Here we have tight junctions, okay, kind of facing the inside of the tubule, and we know that we have all these microvilli. We almost have like a brush border situation going on here, facing the fluid coming through. Okay. So we've absorbed actively sodium towards the blood, setting up a sodium gradient where we have low sodium inside, right? Low sodium, which means we have higher sodium here. And this is also going to be lower than the sodium we have coming through the tubule. Okay. Right. So some of sodium is going to try to follow its gradient, right? Which means it's going to move into our cell towards that low sodium environment, and then it's going to get kicked out by the sodium potassium pump on the other side. Water can follow along, kind of chasing that salt, basically. Okay. Now, as we're pumping sodium into that space that neighbors the capillaries, right? So into this peritubular space, right? Right. Right. So as we move sodium into that space, sodium has a positive charge. So it's going to basically like electrically, magnetically attract chloride ions attracted to that charge. So remember when we talked about like electrochemical driving forces, we're not going to go into detail about those again here, but remember that that can have an effect on ions. So sodium is being actively pumped. Chloride, because of those charges, is following. Means we have a lot of solute there, which means that we have even more of a pull, even more of an osmotic pull for water to move towards this area where we're concentrating these solutes. Cool. So there are lots of diagrams in your book about this if you want to think about different types of solutes that might be reabsorbed and how exactly that would work. But the big picture of what we want to think about is the direction, which for the proximal tubule is for almost everything going to be reabsorption. We're reabsorbing lots of stuff. We're reabsorbing sodium. We're doing that actively. We're reabsorbing water. That water is following the sodium gradient that we're setting up. Okay. So as we move into this next little bit, so we're thinking about reabsorption in the proximal tubule. We said this is unregulated reabsorption. So which of these things are true of unregulated reabsorption? Okay. Yeah, so unregulated reabsorption means that we don't have things like hormones needed for this to happen. So what was happening with the glucose was unregulated reabsorption. What's happening with the water is unregulated reabsorption. What's happening right here with the sodium, unregulated reabsorption. All it means is that these are kind of automatic processes. We didn't need a signal from the brain or from a different organ here. Okay. So continuing with our different directions things can go. Right? So we talked about filtration, so moving into the nephron. We talked about reabsorption, where we have things moving from the nephron into peritubular capillaries. We do also have secretion. So in secretion, this is when we're going to have more of something coming into the nephron later on. So instead of coming in at the glomerulus with the filtration, secretion are coming still from the blood, but from some other part of the bloodstream, going into that filtrate into the nephron here. So the barriers that they'll need to cross are going to be the same as for reabsorption. So we're going to have to cross the cells of the capillary, so that endothelial capillary layer. We're going to have to cross the cells of the nephron, so that renal epithelial cell layer as well. Okay. And our transport mechanisms are going to work pretty much the same as they do for reabsorption, which is to say, you need proteins embedded in the membranes in order to do this, depending on exactly what the molecule is. What's going to differ is really just the direction they're pointing, the direction they're moving stuff. So substances that we see secreted in the nephrons, not going to be sodium, but unsurprisingly, whatever sodium does, potassium likes to do the opposite. So sodium reabsorption, potassium will be secreted. Hydrogen ions also get secreted. So do choline, creatinine, so do medications like penicillin. So we will see some additional components being added in to the filtrate in the nephron as we move further along. So here you can see a table from your book about what gets reabsorbed and what gets secreted and where. So I do recommend kind of keeping this in your big picture sort of view. So you can see here how the proximal tubule is reabsorbing like practically everything. The only thing we see secreted in the proximal tubule are hydrogen ions. So we mentioned hydrogen ions are part of pH balance. So we actually saw some of that secretion of hydrogen ions as we were looking at some of the ways that we reabsorb bicarbonate. Happen to be in some of those pictures. So as we move into the loop of Henle, we're going to see in the first part, in the descending limb, we're going to reabsorb water. In the ascending limb, we're going to reabsorb a bunch of ions. No secretion happening here. When we get to the distal tubule, we're going to keep reabsorbing, right? We'll do a little bit of secretion in both the distal tubule and the collecting duct. Still just going to be those hydrogen ions, but now also potassium. Okay. So these are under typical conditions, things you would typically expect to see secreted will be hydrogen and potassium. The other parts are going to be dependent on how your body is functioning, what exactly you have in your body. For the most part, we're focusing on reabsorption. All right. So since we think about unregulated reabsorption in the proximal tubules, it is important to realize that we do have regulated reabsorption and secretion as well, right? So that's why we bother specifying that in the proximal tubule it's unregulated, because as we get to the end of the nephron, we're making fine-tuned changes to the concentrations of various substances in the urine and into the volume of the blood. This is where essentially hormones come into play. So when you get to the distal tubule and to the collecting duct, we're going to start basically seeing commands coming in, telling the cells of the nephron what they should and shouldn't allow to cross their membrane, which is going to have the effect of regulating whether they're reabsorbing something and how much they're reabsorbing. Okay. So that's what we mean when we say regulated transport across the epithelium. We'll be talking about the specific hormones involved when we talk specifically about what's going on with water and water balance and blood volume, and also when we talk about sodium and potassium balance and how that interacts with the bloodstream as well. But just to notice that because we're doing regulated reabsorption in the distal tubules and collecting ducts, their cells are going to look a little different. Right? We're not our bulk reabsorber anymore, so that apical membrane doesn't have that big brush border. You can see this is a little more stunted looking. We have prominent mitochondria here, because as we think about this regulated reabsorption, we're going to need to be actually actively making new transporters some of the time. So we're going to want to make sure that we can use energy to actually make stuff here. And we're going to have tight junctions. So these coffee beans have really fully closed up in between. So we've got a tight seal here when we get to the distal tubule and the collecting duct, so that we're really forcing things to go through the whole cell so that we can only reabsorb or secrete when we need to. That's just zoomed in on those cells. Okay. So when we talk about water reabsorption in particular, we're going to be talking about the structure in the middle of the nephron called the loop of Henle. So that's this kind of hairpin in the middle here. Okay. So what this does is it establishes conditions in the kidney necessary to concentrate urine, meaning it's going to actually change the properties of the kidney And specifically, it's going to be changing the osmolarity and the osmotic gradient of the kidney as we move through the kidney so that we can use that osmotic gradient to reabsorb even more water when we want to. Right? So you can see that this loop is traveling here into deeper parts of the kidney. So it's kind of setting the stage for what environment we're going to pass through as we pass through, especially here, you can see the collecting duct passing down through that same area as the loop of Henle. Okay. But before we get there, let's just mention excretion rate and clearance, and then we'll focus on our different substances one by one. First, we'll talk about water on Wednesday, and then we'll talk about sodium and potassium if we get there. Okay, so our final renal exchange process we're thinking about is excretion. So excretion is just how much of the substance is literally leaving your body. So if we wanted to think about an excretion rate, we'd have an amount, right? So the amount of substance excreted. And that has a relationship to the processes going on earlier on in the kidney, all right? So if you are going to look, the amount of a solute that's excreted, that solute got into the kidney in the first place, got into the nephron in the first place through filtration. And so here we see a situation where we have 12 millimoles of a solute filtered, that filtered load up here at the beginning of our nephron. And we can see that in the urine here, we have our amount excreted as 9 millimoles, right? So we can tell that we didn't keep all that solute that we filtered, all right? So some amount of it was surely reabsorbed. In this case, we also had an amount that was secreted, but less than the amount reabsorbed, which is why this excretion number went down. Okay, so we'll pick up here on Wednesday with an example.